All right, good afternoon, class. This is lesson 19, covering section 4.6 of our textbook. So we're finally going to be wrapping up chapter 4. And this last section of chapter 4 we're discussing, we've talked about bases, the plural bases. We've talked about bases, um, how to rewrite a vector in terms of a basis, the b coordinate vector, for example. We've discussed that. And we've discussed the importance of having a different basis where a basis may represent some kind of in-place system. Um, for example, we've discussed like a propulsion system on a lunar module. The way the engineers design it, um, the engine thrusters, where they're pointing, the direction of those thrusters, those are going to be pointing in particular vectors, and the vectors they're pointing in might not be the identity vectors, right? So that's going to give you some basis for the space you want your module to be able to traverse. Well, then you need to calculate, if you're one of the engineers or programmers designing the flight path for the module, then you would need to know how much or how long each thruster needs to be turned on for in order to get the module to land where you want it to land, right? Um, Now, of course, what we haven't discussed yet is, well, what if you already have a solution in one basis and you want to rewrite it now in terms of another basis? You can imagine, again, going to the lunar module example, maybe you have a solution for a current module, a lunar module, and you know how you need to maneuver the module to get it to land where you want. But now engineers come along, they design you a new, better, fancier lunar module. But now this newer model, maybe its propulsion system, it's using different vectors than the original model was. Maybe there are some vectors they like better, or maybe there were just vectors that were easier to work with when they were designing it. Whatever the case, this new model could be using a different basis than your original model. Well, now your flight path you have created for the first module is not going to work for the second model. Why? Because they have two different bases, right? And so what works for one basis where the thrusters are pointing in different directions might not work for the second one where the thrusters are pointing in different directions. Um, so you would need to change your flight path for the first module, the old model, and redesign your system to work for the new model. So how do we do that? How do we change a vector that's already in terms of one basis and change it into another basis? That's what we want to look at today. That's what we want to be able to do by the end of today's lecture. All right. So this is section 4.6. And as you might guess, the title for this section is change of basis, right? We want to go from one basis to another. So let's go ahead and just look at an example, and we're going to piece this together one step at a time, and then I'm going to give you the theorem, which tells you how to do it. But the theorem is going to come from exactly what we're about to do. So let's say basis 1 is the set of these vectors 1, 0, 1, 2. And again, I'm doing this in the two-dimensional case just for the sake of ease. But the way you solve this in 3 dimensions, 4 dimensions, 5 dimensions is the exact same problem, right? So let B1, basis 1, be this set of vectors. And let's let basis 2 be the set of 1, negative 1, 1, 1, right? And both of these are, in fact, a basis because, well, they're linearly independent. And I have 2 pivots, so this spans R2. They're linearly independent. They're not multiples of each other. I have 2 pivots, so this spans R2. These are both a basis for R2. Okay, great. Now we can say, let's let x equal the vector 2, negative 4. You can imagine, as we discussed in yesterday's work in 4.5, x could be the target location we're trying to reach, right? In terms of the standard basis, recall what is the standard basis? Well, these are the identity vectors, right? Or the vectors taken from the identity matrix. We know that any vector rewritten in terms of the identity basis is just the same vector. It doesn't change, right? So this could be the target location. But now we would like to know, okay, how do I get to 2, -4 via a combination of these vectors? What combination of these vectors, or the combination of this propulsion system where the vectors are pointing in this direction? Of course, this is a two-dimensional example. So this is more like a, suppose you have a robot with some designed wheels, but the wheels, instead of being able to turn, are pointed in some different vectors, and you can only roll in one direction of a vector or roll in the direction of another vector. All right, a little limited, but basic robotic programming often starts with a simple system like this. All right. Okay, so we want to know what combination of these two directions is going to get me to 2, -4. Well, this is just like yesterday's work. How do we solve this? Well, we're trying to know, so far it's just a review of yesterday. We're trying to know what combination of these vectors, what combination, well, that's the x in terms of B1, will equal x. How do we solve this? We need to row reduce the augmented matrix. We're going to augment with x. Now, lucky for us, this is already in an echelon format, but in my lecture notes here, I already have the reduced form, so I'm just going to go ahead and write out the row reduced echelon form. And we have 1, 0, 4, 0, 1, -2. So in fact, x in terms of B1 equals 4, -2. In practice, what does this mean? Okay, good. I still have space. What does this mean? This means x equals 4 times 1, 0 plus -2 times 1, 2. And lo and behold, here's my x. And yeah, this works out. I get 4 minus 2 is 2, 0, -4. Great. So this is telling me how long each of these directions have to be turned on in order to reach the vector 2, -4. Okay, great. Again, this is just a repeat of yesterday's work. This tells us the B1 coordinate vector of x. Now, what if I want to instead find the B2 coordinate vector of x? Okay, well, there's two ways to go about this. Option 1 is to just rinse and repeat, do the exact same process, right? Instead of trying to find the combination of the B1 vectors, I want to find the combination of the B2 vectors. So we have P sub B2, this was our notation from yesterday. This is the matrix which is created from the B2 vectors times x in terms of B2 equals x, right? How would we solve this? Well, just like we did with B1, we would take the matrix, augment with x, and then row reduce, so on and so forth. What I'm getting at here is that if we go ahead and solve it this way, I'll go ahead and give you the answer. The B2 coordinate vector of x is 3, -1. And we can double check, does this answer make sense? Well, this is saying this is how long each of these vectors have to be turned on in order to reach 2, -4. So does that work? Well, this claims that x equals 3 times 1, -1 plus a -1 times 1, 1. Does this work? 3 minus 1 is 2. -3 minus 1 is -4. Great. So this is the B2 coordinate vector of x. All right. So now we want to think about the question. This is all fine and good, but now, as we were discussing earlier, imagine you already have the flight path. So here's our hypothetical flight paths using the first basis, the hypothetical flight path using the old model, the older lunar module. But I want to change this flight path, and I want to be able to jump to this flight path, right? Now, on one hand, we know, okay, sure, you could just recalculate the entire flight path, right? And for the case of this kind of problem, that's not so hard to do because it's only one calculation, right? Now, you might imagine if it's a more complicated problem, like a flight path to land on the moon, that's not just a single calculation, right? You're running hundreds, if not thousands of calculations, in which case you really don't want to redo all thousands of those calculations. Instead, we would like a nice and quick way to change from the B1 coordinate vector, and I want to be able to change it without too much work into the B2 coordinate vector. How do we change between these two vectors? All right, that's what we're trying to answer here. Okay, so let me make some space here. All right, and I'm going to write these up here. We're going to need them later because this is how we're going to know if our solution works. I want to change the B1 coordinate vector of x. I want to somehow change it into the B2 coordinate vector of x, which is 3, -1. Okay, so I put that off to the side. Let me erase this, make some space. All right, so how are we going to do this? Well, first, I want to go ahead and make a note of the following pattern because this pattern is going to be very useful in just a moment. Let's say, so this script B1, this is the first basis. Let me call these basis vectors B1 and B2, lowercase b1 and b2, right? Remember, lowercase letters can be vectors here. So b1, b2, these are my vectors of the first basis. And I just want to go ahead and notice this following pattern. B1 equals 0.5 times 1 - 1 plus 0.5 times 1, 1. Okay, now how did I get this? This is the same thing as saying what combination of the B2 vectors gives me B1, right? So you could solve this if you wanted to, right? You could take your B1 vectors and you want to solve for B1 in terms of the B2 basis. You want to know how does this happen? Well, you could go through this whole process and double check my answer here. But long story short, I'm skipping over all the steps here just for the sake of time. But this is what's happening here, right? This is how you find B1 in terms of the other basis. Why does this matter? Why would this be an important piece, right? ... Why would this matter? Well, if I'm trying to change a vector from one basis into a vector of another basis, it might be helpful to know how are my basis vectors rewritten in terms of the basis I'm trying to go to, right? So, okay. What does this tell us then? This tells us B1 in terms of the second basis, the basis I'm trying to go to, equals 0.5, 0.5. Similarly, what about B2? That's the second vector of the first basis. Well, B2 can be rewritten as negative 0.5 times 1, negative 1, plus 1.5 times 1, 1. And so B2 rewritten in terms of the second basis, the B2 coordinate vector of B2 is equal to negative 0.5, 1.5. All right. So make sure you understand this little step here, because this is going to help us answer the question in just a moment. All right. So the claim here is that we've done all the work we really need. How is this going to help us? Well, notice, let's suppose I only tell you the B1 coordinate vector, and let's cover up the B2 coordinate vector of x. Let's suppose we don't know what this already is, right? We already calculated it, so we'll know what the answer should be. And we'd like to say, okay, how do I find x rewritten in terms of B2? How do I go from this vector to this vector? Well, we already know x is a combination of the first basis vectors, right? X equals 4 times little b1 plus, oh wait, did I make a typo here? I did. X in terms of b1, this is for negative 2. The negative does matter. Right. Okay, 4b1 minus 2b2, right? But this is just what we already knew. It's what we already had calculated before. This is the b1 coordinate vector of x. It's telling us what combination of the first basis vectors gives me the x that I'm trying to reach, right? Okay. But now, what can we do? Well, like we saw yesterday, the act of changing a vector into another basis coordinate vector, this is a linear transformation, right? Why? Because as we saw yesterday, to transform a vector into its b coordinate vector is the same thing as solving an augmented matrix. It's the same thing as solving a matrix equation. So the act of changing 4b1 minus b2 into the script b into the second basis, this is a linear transformation. This is a linear operation, which means bilinearity, I'm running out of space, bilinearity, let's see, did that fit on the screen? Kind of. Okay, you get the idea. Bilinearity, we can do this next step, which says, well, because it's a linear transformation, I can pull this apart. This is 4 times b1 in terms of b2 minus b2 in terms of b2, right? But now what has happened, this is just a linear combination, right? I'm taking 4 times this vector, which we already know what that vector is over here, minus this vector, which again, we already know that vector, it's over here. This is a linear transformation, or a linear combination. In other words, I can rewrite this as matrix multiplication, where b1 in terms of the second basis is my first column vector, b2 rewritten in terms of the basis is my second column vector, and I'm multiplying it by this vector 4. Wait, did I make a mistake? Yeah, this should be negative 2. Gosh darn it. Negative 2 times this vector. This is telling me what combination of the columns is supposed to equal this b2 coordinate vector. Now, this is where it's helpful. We've already calculated b1 in terms of b2, b2 in terms of b2. This is the multiplication. 0.5, 0.5, negative 0.5, 1.5 times 4, negative 2. Now you just multiply the matrix times the vector, and we get out 3, negative 1. In other words, what have we shown here? So let me erase some of this so we can highlight what we did. What we have shown is that if we're trying to find x in terms of another basis, well, first of all, that x, if we already know what it is in terms of a different basis, that x is a combination of the other basis, the first basis. But if I'm trying to rewrite that in terms of a new basis, I can apply linearity. This is the same thing as taking this linear combination, which is the same thing as this matrix multiplication, which is the same thing as saying if you ever are starting with a vector in terms of one basis, well, if you want to change it into another basis, then you have to find what the vectors of the first basis are in terms of the new basis. I'm running out of space. Hold on. Let me write this differently. Right. What did we do here? We found the basis vectors of B1, and we're rewriting it in terms of the second basis. Right? This is what we did in this step right here. That's what this combination is. So if you're trying to go from one basis to a new basis, you need to know what your original basis vectors are changed into the basis you're going to, which makes sense. If you're trying to change from one basis to another, you need to know how your basis vectors can change into the new basis vectors, right? In other words, this is going to be our formula for changing from one basis to another basis. Now, this is all written up a little bit nicer as a theorem, and we're going to write out that theorem next. But I want to highlight this matrix that we just created. We've been using capital P, and there's a reason for capital P. This is going to become more apparent in Chapter 5, because we're going to find out capital P. It also has other applications, other meanings. But capital P here, this was the matrix we created, which transforms B1 vectors into the B2 vectors, right? So how do we memorize this order? Well, whatever is on the right side, this is what you're multiplying by. Whatever is on the left side, this is the output of that multiplication. So I take a B1 coordinate vector, I multiply it by this matrix, and it changes it into a B2 coordinate vector. Okay, so we're ready for the theorem. Let's go ahead and take a look. Okay, so what's this theorem? So this theorem states, let script B, this is some basis, B1, B2, dot, 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 Bn. And let's let script C be a different basis. This is C1, C2, dot, 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 Cn. Notice, if they're both a basis for the same space, they're going to have the same number of vectors. They both have an n number of vectors. So let B and C be bases for a vector space, capital V. All right. What's the punchline? Well, then there exists a unique n by n matrix. And notice this is square, which is nice. That means we can do all the square stuff we need with matrices, or at least with square matrices. And verbal matrix theorem will apply. P from B to C. Okay, let me make sure it's still on the screen. It is, great. Then there exists a unique n by n matrix, P from B to C. What does this matrix do? Well, this is the matrix such that transforms let me just write this out and we'll talk about it. Okay. This is the formula we have. This is the same formula we had right here. If you're going from B to C, that means you're multiplying by a B coordinate vector of x. And by multiplying with this matrix, it changes it into the C coordinate vector of x. This is the formula which will allow us to change a vector in terms of one basis and change it into another basis, right? In particular, what is this matrix? Well, just like we did in the example, the matrix which changes from B into the other basis, I have to know how are my B vectors, that's the basis I'm starting in, I have to know how each of those vectors are rewritten in terms of the basis I am going to. So this is our formula. This is the big take home from today's lecture. If you're trying to go from one basis to another, if you're trying to go from a B basis to a C basis, well, then you have to plug in your B vectors and rewrite them in terms of the basis you're trying to go to, right? Now, there are some nice things to note about this. First of all, by our definition for a basis, my B vectors are linearly independent, okay? My C vectors are also linearly independent. And the act of changing a vector into a new basis, that is a linear transformation. We did that yesterday. So what am I getting at? This transformation from B1 to C1, B1 in turn, what combination of the C vectors? This is a linear transformation. So when I transform, this is going to preserve the linear independence of my B vectors. Rewriting them in terms of C is just a linear transformation, and linear transformations preserve linear independence. So these new columns I'm creating are still linearly independent, which means this matrix is invertible. Why would we like that? Well, if this matrix is invertible, that means I can multiply by its inverse. So note P from B to C inverse exists. In fact, it will always exist because our basis vectors are linearly independent, right? So what's nice about this? Well, if I multiply by the inverse of the P matrix from B to C, I'm going to multiply on the left side, and I have to multiply on the left side. It's the only way to cancel. I've been grading a lot of the midterms, and it looks like a lot of students are confused with the idea of matrix multiplication with matrix equations. You have to multiply on the same side for both sides of the equal sign. In order to move PBC to the other side, I have to multiply by PBC inverse on the left. I have to. If I multiply on a different side, that's not going to cancel anything. If I multiply on a different side, it's not going to give me a different answer. Or I'm sorry, it's not gonna simplify the problem, right? If I want to remove this P matrix, then I have to multiply by its inverse on the left side. That is the only way to remove it. Okay. But long story short, what is a matrix times the inverse? That's just the identity. What's the identity matrix times a vector? It's just the vector. So what do we have? The inverse of the matrix from B to C now tells me how to change vectors in terms of C into the B coordinate vector. In other words, regardless of which direction you're trying to go, whatever direction you need, they're just inverses of each other. The inverse of PB to C is the matrix that takes C and changes it into B. Right? That's exactly what's happening here. This matrix times the C coordinate vector equals the B coordinate vector. So if you find your matrix from B to C, the inverse of that matrix is the matrix from C to B. Right? You see the letters swapped here. So these matrices are inverses of each other and allow you to go back and forth between the two. Okay? And then the last kind of thing I want to highlight here, and then we'll do some examples, is, well, don't forget about the standard basis. What if you want to change a vector to the standard basis, right? What if you want to change from one basis and go back to the standard basis? Well, according to our formula, I have to take my B1 vectors and rewrite them in terms of the standard basis. Let me make sure that's still on the screen. Okay, it is. Great. This is our formula, right? Taken just from the theorem. But any vector rewritten in the standard basis is just the same vector. So that's just B1, B2, Bn. But what's this matrix? This is the matrix where I just took the B basis vectors, and I just wrote them as columns. Well, this is exactly what we did yesterday. This is the PB matrix, right? And we know, what does this matrix do? Well, the whole point of this matrix is that you multiply it with a B coordinate vector, and it gets X. This is also the matrix equation that we use if you're trying to solve for the B coordinate vector. If you know X, but you don't know the B coordinate vector, well, then like we did yesterday, you take the PB matrix, augment with X, row reduce, solve for the scalars, right? So we've done that yesterday. Okay. That's everything that's new in 4.6. All right. So let's take a moment. I want to look at another example and show how we can maybe further simplify this kind of question, right? So we have our formulas. Remember this formula. This is the key thing for today's lecture. All right. So let's suppose I give you a basis B, and I want to rewrite, or sorry, let me first write the basis. My basis is 1, -3, -2, 4. Oh, this is a set, sorry, not a matrix. I'm getting loopy. Right, the basis is a set of vectors. Here's my first basis. Let's say my second basis, C, is the set of vectors -7, 9, -5, 7, right? And so now I could ask you a question. What is the matrix which transforms C vectors into B vectors? What is this matrix? All right. Well, according to our formula, I'm trying to change from C to B, so I need to plug in my C vectors, -7, 9. I'm trying to rewrite them in terms of B. And so this is going to be my answer, right? Now, there's two ways to go about this. Option one, you could go with the traditional solution that we've been using, where how do you find a B coordinate vector of some vector x? Well, you need to find out what combination of the B vectors equals that vector. And when you want to find the other one, well, then you need to find what combination of the basis vectors equals the second vector, right? So you have two different augmented matrices that we have to solve. However, we can actually make this a little bit easier on ourselves by doing both at the same time. How? Well, again, this is a linear transformation. So if I just add a second column, I could solve for both at the same time. In other words, I can combine these into a single augmented matrix where I'd like to know what combination of my B vectors can result in -7, 9, -5, 7, right? And so instead of solving and reducing two different augmented matrices, I can just combine the problem into a single augmented matrix, and we'll reduce this in one go. Now, if you prefer to just do it one at a time, that's fine. Me personally, I tend to do it one at a time just so that I don't confuse myself. But if you want to use this methodology, that's perfectly fine. That can still work, right? But notice this pattern. If I'm trying to change from C to B, and my notation is written in this order, then that means my C vectors are on the right, and my B vectors are on the left. Right? You see how this pattern matches? So this is one reason why we like this notation, why we go from C to B with this arrow from right to left, right? This left pointing arrow. We also like this notation because this matrix is multiplied by a C vector on the right side, right? You look back at the formula, whatever you're starting from, whatever basis you're starting with, you multiply by that vector on the right side, and then it outputs something, right? Okay, so you can put the B vectors and you can combine this into a single augmented matrix like this. Well, lo and behold, if you put this in row reduced echelon form, we're going to get 1, 0, 0, 1, 5, 6, 3, and 4. So in other words, what is this telling us? You can imagine like this is solving for two different equals columns, right? This is telling us, if you're trying to find the different scalars, this is telling us 5 times b1 plus 6 times b2 will give you the first column of C. And then this is saying 3 times the first column of B times 4 times the second column of B will give you the second vector in C. In other words, this right here is the matrix we're looking for, right? Because when you row reduce to the echelon format, your answer is in the equals column. So this is the matrix that we're looking for, right? Now, if you want to find the matrix from B to C instead, well, you could just take the inverse of this and you're done, right? It's a 2 by 2, so find the inverse of a 2 by 2 is not hard to do. And we're golden. All right, so we have this example. Now, lastly, I do want to talk about today's participation question. So let me see. This is participation day 18. All right, so we have let capital F. Oh, let me share my screen. Share screen. Here we go. Okay, we're sharing the screen. Participation day 18. Let capital F be the set of these vectors, F1, F2, and let G be a different basis with these vectors, G1, G2. These are both bases for a vector space, all right? Now let P be a matrix whose columns are the G coordinate vector of F1 and the G coordinate vector of F2. From which coordinate space to which coordinate space does P transform vectors? Well, all we have to do is look back at our formula for today and think about, okay, what am I plugging in? What vector am I transforming? I'm taking my F vectors and I'm rewriting them in terms of a different basis. In other words, I'm changing from F vectors to G vectors. Well, that's exactly what the answer is. From which coordinate space to which coordinate space does P transform vectors? It transforms F coordinate vectors into G coordinate vectors. Okay, so that's our answer for today. P transforms F coordinate vectors. Oops, if I could spell. Coordinate vectors into G coordinate vectors. If you want to get it fancy, you can add these hyphens here. It's not super important. But the idea here is that this is the matrix from F to G. This transforms F coordinate vectors into G coordinate vectors. Okay, great. Submit. And that's all for today's section 4.6. We've finished up chapter 4. So beginning tomorrow, we'll start in chapter 5. And chapter 5 is going to be the last chapter we discuss for this class. Chapter 5 is really going to be the culmination of everything we've talked about in this class. It's going to pull everything together into one chapter, and everything is going to nicely relate to one another, nicely connect. And all our vocabulary terms, they're going to have meanings that connect to one another. In part, we've seen this with the invertible matrix theorem, right? The invertible matrix theorem, we created an extended version and we added more statements to it, and it's relating everything we've talked about, at least for square matrices, right? Okay, that's all for today. If you have more questions, by all means, please do email me. Otherwise, that's all. Best of luck, and I will see you tomorrow.